I consider the conservation of momentum to be one of the 4 core principles in this course. We've already discussed the other 3, kinematics, Newton's second law, and the conservation of energy, so the conservation of momentum completes the list. In this video, we'll apply the conservation of momentum to linear momentum, which is the momentum we discussed in the previous video. We'll discuss angular momentum and the conservation of angular momentum in a later video. So let's start by deriving the conservation of linear momentum equation. Consider a system of 2 objects that are moving toward each other and then collide. When they collide, they apply a force to each other. Per Newton's third law, these 2 forces must be equal in magnitude and opposite in direction, so F1 equals negative F2. If there are no other forces acting on these objects, then each of these forces is a net force, so we can use Newton's second law to replace each force with delta P over delta T. After doing that, the equations become this. In this equation, the delta T's are the same, so they can be canceled out. Next, let's expand each delta into final minus initial, and then move the initial momentum terms to the left side of the equation and the final momentum terms to the right side of the equation, so that it becomes this. Because we've defined the 2 objects to be the system, the net momentum of the system is the momentum of object 1 plus the momentum of object 2, and we wind up with the initial net momentum of the system equals the final net momentum of the system. This is the conservation of linear momentum. Recall that we assumed that there were no other forces acting on the objects other than the forces associated with the collision, which means momentum is only conserved when there are no external forces acting on the system, or if there are external forces, they're small enough to neglect. But as we discovered in the previous video, the forces involved in a collision are typically very large compared to the other forces that might be acting on the system, like gravity and friction. So this is typically a good assumption. I think it's useful to state the conservation of momentum in words as well. The total initial momentum of a system equals the total final momentum of the system when there are no external forces or the external forces are negligible. In practice, when we apply the conservation of linear momentum equation, we will usually expand it into a more practical form. To do this, first recognize that it is a vector equation, so we will apply it in each coordinate direction separately. In 2 dimensions, then, it becomes 2 equations. Also, for the problems we solve, there are typically 2 objects in the system, so the net momentum terms become P1 plus P2. And finally, we'll replace each momentum term with mv. This, then, is the form of the conservation of linear momentum that we typically apply to problems. When we apply it to problems, there are 2 basic types: recoil problems and collision problems. Recoil problems are when the objects are forced apart, and collision problems are when they come together and collide. We'll discuss recoil problems in this video, and we'll discuss collision problems in the next video. For both types of problems, we will follow the same basic procedure. First, draw a diagram that includes the initial and final states of the objects, the velocity vectors, and the coordinate scheme. Then apply the conservation of momentum equation. When we get to the collision problems in the next video, we'll also see that there are several categories of collisions, and there will be additional equations or other facts to apply. The next step is to solve for the unknown and then make sure that the answer is reasonable. Now let's discuss recoil problems when objects are initially together and then get forced apart. Some examples of recoil are 2 ice skaters who are initially standing next to each other and then push apart, or a person standing in a canoe and then jumps off the canoe in one direction, which propels the canoe back in the other direction, or a rocket where the exhaust is ejected in one direction and the rocket then is propelled in the other direction, or an explosion that propels multiple fragments in all directions. So let's wrap up this video with a basic example. A person stands motionless on ice like a frozen pond and fires a gun. Assuming that the friction between the person and the ice is negligible, what is the speed of the person immediately after firing the gun, given the following data? The person's mass is 80 kilograms, the bullet's mass is 5 grams, and the speed of the bullet after being fired is 1,000 meters per second. Per the procedure, we'll start with a diagram. I've decided to call the person object 1 and the bullet object 2. Of course, it's arbitrary which is which, or you can use subscripts like P for person and B for bullet if you'd like. I've indicated that both initial velocities are 0 and the final velocity of the bullet is 1,000 meters per second. The next step is to write down the conservation of momentum equation. Because all of the motion in this problem is in the x direction, we just need to use the equation in the x direction. The initial velocities are 0, so we can zero those out. And then we can solve this for the final velocity of the person, which is object 1, and then plugging in values, remembering to convert grams to kilograms to make the units consistent, we find that the final velocity of the person is negative 0.063 meters per second. Of course, the question didn't provide a coordinate scheme and therefore asked for the person's speed rather than velocity. So the final speed of the person would just be positive 0.063 meters per second. So that brings us to the end of the video. Next time we'll discuss collisions.